Hi, welcome to the recap video for This Week in Stats 220. Last week we learned about type 1 and type 2 errors in statistical testing. So let's briefly review that. There's the truth, and either H0 is true or the alternative hypothesis is true. And then we have the results of the statistical test. Statistical test. And we either reject H0 or we don't reject H0. Don't reject H0. And so if we reject H0, but H0 is actually true, we've made a type 1 error. But if we reject H0 and the alternative is true, then we haven't made an error. So that's okay. And if we don't reject H0, but H0 is true, then we haven't made an error. But on the other hand, if we don't reject H0, but the alternative is true, then we've made an error. And this is called a type 2 error. Now let's suppose that we're testing a hypothesis about a proportion. So suppose that the null hypothesis, H0, is that the proportion P is equal to some value P0 versus the alternative hypothesis that P is not equal to P0. Well, the first thing we can talk about is statistical significance. Statistical significance. Alpha is typically called the type 1 error rate, or the probability of a type 1 error. Probability of a type 1 error. And this is equal to the probability of rejecting the null hypothesis when in fact the null hypothesis is true. A statistical test is significant at level alpha if the p-value is less than or equal to alpha. So for example, if the p-value was equal to 0.03, for example, and let's say alpha was equal to 0.05, then the test would be statistically significant at the 5% level, but not at the 1% level. In other words, since the p-value is less than or equal to 0.05, but the p-value is greater than 0.01, it's statistically significant at the 5% level, but not at the 1% level. The next major concept with type 1 and type 2 errors is the concept of power. Power is related to the probability of a type 2 error. And it's actually equal to 1 minus the probability of a type 2 error, which is basically the probability that you'll reject H0 when you should. In other words, when the alternative hypothesis is true, when HA is true. So we can talk about the power of a statistical test for a specific alternative. So, for example, suppose we were testing H naught, that P is equal to 0.5, and versus the alternative, that P is equal to 0.6. With n equal to 100 subjects, what is the power of this test? Well, we can look at the app to figure that out. So here on the Power app, we have a sample size of 100, and the true probability here, if that's the alternative value, is equal to 0.6, the null hypothesis value is equal to 0.5, and the significance level is equal to 0.05. So I should add one thing in here, that what is the power of this test at the 5% significance level? Well, the power in this case is 0.521, and that's over here. A power of 52% isn't that large. So for example, if the null hypothesis value is 0.5 and we wanted to detect an alternative value of 0.6, then there's only about a 52% chance of the statistical test being able to do that. So how can we increase power? Well, we can increase power by increasing alpha. So let's say if we increase alpha, what happens? So if we increase alpha to, let's say, 0.1, now the power goes from 0.52 to 0.644. So it's increased. Of course, leaving everything else fixed. We can increase the alternative probability. So we can increase alternative hypothesis value. So let's go back to 0.05 here and increase from 0.6 to 0.7. And now the power is 0.984, so we've gone from 0.52 to 0.984 just by looking at an alternative value of 0.7 instead of 0.6. The next thing we can do, which is the most practical thing to do, is increase the sample size. So let's go back to 0.6 and increase the sample size to 150. Let's add 50 subjects, or 150. Now the power is 0.694, so we've gone from 0.52 to 0.694. So increase sample size. So these are strategies to increase power. The third thing that I want to discuss is the relationship between statistical tests, two-sided statistical tests in particular, and confidence intervals. So for this example, suppose we survey 200 expecting mothers and 91 of the mothers correctly guess the sex of their baby. So a 95% confidence interval. So p hat, in this case, the sample proportion is 91 out of 200. A 95% confidence interval is 0.39 to 0.53. Now let's suppose we wanted to test H naught, the p is equal to 0.5, versus the alternative, that p is different from 0.5. What information does the 95% confidence interval tell us about rejecting or accepting this null hypothesis? It tells us that the p-value is greater than 0.05, since the null hypothesis value is in the confidence interval. The p-value is greater than 0.05, since p equal to 0.5 is in the 95% confidence interval. What if we were testing this null this hypothesis, that p was equal to 0.7 versus the alternative, that p is not equal to 0.7? What does the 95% confidence interval tell us here? Well, it tells us that the p-value is less than or equal to 0.05, since p equal to 0.7 is not contained in the 95% confidence interval. So what is the relationship between two-sided hypothesis tests and confidence intervals? Well, here it is. So in general, a 100 times 1 minus alpha % confidence interval has the following properties. 1, alpha is the probability of a type 1 error. The second property is that if the null hypothesis value is contained in the 100 times 1 minus alpha % confidence interval, then we cannot reject H naught at level alpha. If the null hypothesis value is not contained in the 100 times 1 minus alpha % confidence interval, then we can reject H naught at level alpha. So that's it for this week in Stats 220, and I'll see you next week online. Bye for now.